All right, so today I'm going to go over substitution reactions. All right, so a substitution reaction is essentially a reaction in which you have two species. One of them has an entity, such as an atom on the molecule, that leaves, in which then the other species comes in and replaces that. Hence why it's called a substitution reaction. So just to give you a picture of what this might look like. So say you have an alcohol with an anion, all right? What's going to happen is that alcohol is going to leave and the halogen is going to come in and take its place. All right, so you have a species that replaces something that leaves on your reactant. All right, hence the name substitution reaction. All right, so there are a few things that I want to go over to help paint a picture of everything that you essentially would need to know for substitution reactions. All right, so I'm sort of going to break this down into Sn1 versus Sn2. All right, so first and foremost, all right, the steps or the mechanisms involved in which these occur. All right, an Sn1 reaction is going to occur in two steps. All right, so it's going to occur in two steps. And why is because the leaving group, or the thing that's going to get replaced, that leaves, in which that creates a transition state. You have a carbocation, in which I'll show an example of that. But you have a carbocation, all right, that's the intermediate, in which then the other species will come in and replace that. Contrary to Sn2, that occurs in one step. All right, so the thing that leaves and the thing that comes in and takes its place all happen at the same time. All right, so you have a intermediate with Sn1, but you do not have that with Sn2. Okay, what about rate? All right, what about the rate law? All right, so the rate for Sn1 reactions, all right, depend upon just the leaving group. All right, just the leaving group, and they are first order. All right, so if you remember from general chemistry, all right, this is where this kind of comes back, but it's not as emphasized in as much in organic chemistry. But if you were to double the reactant, the concentration of your leaving group in the reaction, then you would also double the rate in which it would occur. Okay. Contrary to Sn2, that depends on both the leaving group, and I have the shorthanded as Nu for nucleophile. All right, that depends on the leaving group and the nucleophile. All right, and this is second order. All right, so if the concentrations of the leaving group and the nucleophile double, then the reaction rate will end up quadrupling. All right, that's the difference between a first order reaction rate versus a second order reaction rate. Right, this isn't too much, this isn't that emphasized in organic chemistry. Organic chem, we focus more so on the reaction mechanism itself rather than the rate, but hopefully that is essentially as much as you would need to know, at least here at FAU organic chemistry. All right, substrate. All right, substrate. All right, that's the thing with the leaving group. All right, so just to paint a picture again. All right, having OH be the thing that leaves, that's what we call the leaving group. All right, and the substrate is the thing that was on. All right, that's what we're referring to here as substrate. All right, the substrate is the thing that where the leaving group leaves from, and the nucleophile is the thing that comes in and takes its place. All right, so the substrate for Sn1 reactions really love tertiary. All right, that's the best, then secondary, then primary. Contrary to Sn2 reactions that really love primary, then secondary, then tertiary, in which that's not really ever going to happen. All right. So this leaving group would be considered, or that alcohol classification would be considered secondary. This one would be considered tertiary. And that OH would be considered primary. All right, and I'll label these to leave those there. All right, and the reason why Sn1 loves tertiary substrates is because Sn1 are all about stability of the carbocation. All right, so you should have learned earlier in organic chemistry that the tertiary is the most stable, and lastly, primary is the least stable. All right, Sn1 cares all about stability, contrary to Sn2, that cares more about steric hindrance, or the space that it takes for something to come in and take its place. All right, so intuitively, it's easier for me to walk just through a single file line, contrary to me trying to walk through a heavy crowd. All right, this tertiary carbocation is crowded out by these methyl groups. So it would be harder for a nucleophile to come in and take the place in order to attack that carbocation. So, and the term that we typically use for that is something called steric hindrance. All right, so Sn2 reactions do not like steric hindrance at all. All right, we want as least space being taken up as possible around the carbocation for the nucleophile to come in and take the place of the leaving group for Sn2s. Contrary to Sn1 again, it doesn't care about steric hindrance. It really loves the stability of a tertiary carbocation. All right. Then we get to nucleophile. All right, we get to nucleophile. All right. Sn1 reactions will tend to favor, or the nucleophiles that will tend to favor a Sn1 reaction will tend to be fairly weak. Right? It'll be a fairly weak nucleophile. All right. So things that are generally neutral have a neutral of a charge. All right. Contrary to Sn2 nucleophiles, that will tend to be favored by strong nucleophiles, which tend to be things that are more negatively charged. Okay. The stereochemistry is something that we do need to consider. All right. So the stereochemistry, those that love chirality, all right, it does come back a little bit. In Sn1 reactions, we do something in which we call it the products retain and invert the stereochemistry of the leaving group. All right, so we have retention and inversion. And because of that, we're going to have a mixture of then R and S enantiomers of our product. All right, contrary to Sn2, it only inverts. All right, so say you have this substrate again. So this substrate, say, is wedged. All right, say that leaving group is wedged like I drew up here. All right, if an SN2 reaction were to occur, then your product is going to be dashed, and that's going to be your main primary product, dashed. All right, it flips the stereochemistry. So if you have a leaving group that is wedged and an SN2 reaction occurs, and it's going to end up being dashed, and vice versa, contrary to SN1, which retains and inverts stereochemistry. So you're going to end up with a mixture, and predominantly a racemic mixture, a 50-50 split between R and S. So if you have a wedged leaving group and you have a, you have a wedged leaving group and a SN2 reaction or an Sn1 reaction that occurs, then you're going to have a product that is both wedged and its cousin both dashed. All right, and that's going to create a racemic mixture. Right, so say on your test, you have answer choices in which it gives you the reaction or the reaction that's occurring, and it asks you which of the following is the most appropriate product. All right, and if it's an Sn1 reaction, then it's always going to have a mixture. All right, so you'll probably see an answer choice that says this product plus its enantiomer, that would be appropriate for an Sn1 reaction. Sn2s, again, we don't have multiple products. We have one main product, which flips the stereochemistry. Okay. We have solvents that we got to consider. All right. So the type of solvent that you want the reaction to occur in to favor an Sn1 reaction will tend to be polar protic. All right, so a polar molecule that also has or is capable of hydrogen bonding, polar protic. All right, versus Sn2, a solution or a solvent that will tend to favor an Sn2 reaction will be polar aprotic. All right, so you need polar molecules or a polar solvent to occur in either of these, but the types that favor one or the other, again, Sn1, polar protic will tend to favor an Sn1, in which what I like to just think of that as is if you have a polar molecule that is capable of hydrogen bonding, that's what I tend to define as polar protic. Versus polar aprotic will be a polar molecule, but there's not really any hydrogen bonding. Right? And so let me try to share my screen so that you guys can kind of take a picture of this. All right, so if you can see my screen at all, this is basically what we've gone over so far, but in table format, kind of put all together. All right, so take a picture of that or anything that you need, because we're going to be referencing this to come. Go back. And get a little bit more detailed. Okay. So let me just erase this. All right. So what makes a better leaving group than others? All right. So the best leaving groups are more electronegative. I'm shorthand that as En. And they're larger. All right. All right. So, for example, if you and your buddy went climbing, one of you slips off the cliff, am I more likely to hang on to my buddy that's 100 pounds or 300 pounds? I'm more likely to have to let go of the one that's 300 pounds. All right. So, in terms of an analogy for leaving group. All right. So, the bigger and the more electronegative. So, remember the trend for electronegativity is like that on the periodic table, fluorine being the most electronegative. All right. However, polarizability is favorable And what we mean by that is that's where we get into size. All right, so say you have the halogens, because halogens are a very common leaving group that we see. All right, so say fluorine, chlorine, and so forth. All right, despite fluorine being more electronegative slightly than chlorine, chlorine is bigger. All right, it has a bigger atomic size compared to fluorine. All right, and so its negative charge is more polarizable, it's more stable. If you remember ARIO from acid base concepts, all right, essentially the most acidic leaving group is the best leaving group. Okay, all right, so if you were to rank some, in fact, let me just show you an example of this. Share my screen. If you were to rank or have to rank, and most organic chemistry exams, you tend to have to do this. All right, so the more polarizable or the larger, and the more electronegative, electron withdrawing, the better the leaving group. Essentially, which one is most acidic? All right, this one I wanted to include because that's something called an autosolate. I'm probably mispronouncing that, but we tend to shorthand that as OTOS or OTS. If you ever see that come up, that's one of the best leaving groups that you can have. Not much can top it. All right, it's big, it's electronegative, it's acidic, it's going to want to leave. Okay, but for example, if you're comparing I versus F, they're both in the same column, but I is bigger. All right, so that's going to take the bait. Same if you're looking at the same period, right? Like oxygen versus nitrogen, oxygen is better because it's more electronegative. All right, it's more electronegative in that sense than it is than nitrogen is in size. All right, so the more electronegative and the bigger, the better. All right. Again, if you're halogens are a very common example, which is why I have these up here. So again, like chlorine versus bromine. All right, bromine is in similar electronegativity to chlorine, but bromine is also bigger in atomic size. So that's going to take the bait in terms of which is a better leaving group. Right. Let's go back and talk about nucleophile and bases. All right, so I'm not going to spend as much time going over the differences between a nucleophile and base, but in a nutshell, the nucleophile acts, a molecule that acts as a nucleophile is one that's going to come in and bond with, or it's going to use its lone pairs to make a bond with the carbocation. For example, say you have NH3, right? And you have this substrate, all right? For example, all right? This lone pair on the nitrogen is going to act as a nucleophile via making a bond with the carbocation. All right, so this leaving group is going to leaving there a positive or a partial positive on that carbon. And so our curved arrows, remember from acid base, is always the direction in which electrons are going. Okay, so the electrons on this nitrogen are going to go to that carbocation making a bond. All right, so this nitrogen is acting as a nucleophile in this case, versus it acting as a base in which it can. So say you have an H3 again, but you're reacting with something like HCl. All right, bases, again, going back to our basic acid-base definitions, it's going to go and want to take that hydrogen. All right, so that HCl is going to give up its hydrogen, and that lone pair is going to go get or make a bond with that hydrogen. All right, So that's a very broad overview of the difference between a nucleophile and a base. They both behave very similarly. It's just that a nucleophile tends to be a species that's going to go make a bond with the carbocation on a substrate versus a base that's going to behave as though it's going to go get a hydrogen. Right? That's generally the way that I like to look at it. All right. So what's something that tends to make a nucleophile better than another nucleophile is the larger the atom and smaller molecular size. Okay, so the larger the atom and the smaller molecular size will tend to make a better nucleophile. Okay, so remember, space matters. You have a species that's going to come into a molecule to try to take the place of something. So if you have, say, what we call a tert butoxide versus just that, all right, this is of a smaller molecular size. This molecule as a whole is smaller than this one. So this one is going to find it easier to come in to a crowded area and take the space or replace the leaving group that was there on another molecule. All right, that's why smaller molecular size will tend to make something a better nucleophile. Okay. And I wanted to just touch real quick back on the solvents. All right, let me try to bring up a couple examples. Share my screen. Okay, all right, so there's some very common organic chemistry polar aprotic solvents that I wanted to bring up. These are not my own drawings. I did obtain this from another source. So, but I wanted to illustrate this because these are very common, all right? You commonly don't need to know, again, every professor is a little bit different, but at least here at FAU, our professors don't write out dimethyl sulfoxide, they'll just write DMSO, all right? And you'll tend to, at least in organic chemistry, you'll tend to see the solvent being on the lower half of the arrow, and you'll tend to see the nucleophile being on top of the arrow when you're looking at a reaction. All right, so again, polar aprotic, all of these molecules are polar, but they're not really exhibiting hydrogen bonding. All right. Versus protic, I might have just misspoke, but polar protic is something that is polar, just like polar aprotic, but polar protic is in fact something that does exhibit hydrogen bonding. Okay. And the reason why, let me go back. Sharing. The reason why these work are the example that I tend to like to use is for Sn2s. All right. So just you don't really need to understand why the polar aprotic solvent favors an Sn2 reaction, but that's something that you need to know. But for those that are interested, I'll describe it. So the reason why that is because aprotic solvents don't tend to exhibit a behavior of stability. All right. So for a strong nucleophile, so those with a negative charge, kind of like this or chlorine, all right? These are both considered strong nucleophiles, all right? And they remain free and untouched as a negative anion in solution because you have a polar aprotic solvent, all right? So if there was a polar protic solvent, so something that is capable of existing or capable of doing hydrogen bonding, those things are going to want to react with the solvent rather than having specificity towards the carbocation. All right, we want our anions often that we get from dissociated salts, we must have those remain as a anion negatively charged instead of reacting with a polar protic solvent, which would hinder its ability to remain as a anion. Okay, so you don't, I doubt that you ever really need to have to understand all that of the why, but for those that are interested, by all means. Right. So what I want to now get into is how we determine, or the logic. The logic that I want people to use is the following. So first and foremost, we want to, how do we determine if something is a Sn1 or an Sn2 reaction? So the first thing that you need to look for, not primary, but the first thing that you need to look for is in the stepwise process is the substrate. All right, the substrate. If the substrate is a primary leaving group or a carbocation, it will predominantly have an Sn2 reaction. All right, so if it's primary, it's going to be Sn2. If it's tertiary, it's going to be Sn1. Why? Again, primary carbocations have less and less steric hindrance that favor Sn2 reactions. Contrary to Sn1 reactions, they really like the stability of a tertiary carbocation. All right, but if you're in that middle ground of a secondary carbocation, then we need to look at the nucleophile. All right, if it's a strong nucleophile, so something that will tend to be a negative charge, it's going to predominantly produce an Sn2 reaction. All right. If you have a secondary carbocation with a weak nucleophile, something that tends to be neutral, then it will predominantly produce an Sn1 reaction. All right. So again, primary substrate will tend to produce an Sn2. Tertiary will tend to produce an Sn1. But if your substrate is secondary, then you get into this gray area that you need to really look at whether or not the nucleophile is strong or if it's weak. And if it's a strong nucleophile, then you're going to produce an Sn2. And if you're a neutral or a weak nucleophile, you're going to produce an Sn1 reaction. Okay, so that's the logic that I want you to walk through. All right, so if you're looking at a substrate and you have something that you're reacting with it, that's the logic that I want you to walk through in your head, prompt yourself, think about to determine if this is going to be an Sn1 reaction or an Sn2 reaction. Okay. Now, I'll give you a couple examples. Okay. So let's say we got this. Okay. So that's our substrate, and say we have this salt. And we got a solvent, so say. All right. And say the question is, okay, what's the type of reaction that's going to occur? And what's going to be, what's the product? Okay, so let's walk through that logic again. This logic is the substrate primary, secondary, tertiary? How many carbons? So the chlorine, you have a carbon that's bonded to the chlorine. The Chlorine's gonna be the leaving group, okay? How many carbons is that bonded to? 1, 2. Okay, so we got a secondary substrate that falls into that gray area. All right, so now we need to look at the nucleophile. Is the nucleophile strong or weak? All right, as of right now, it looks weak. However, all right, remember, like dissolves like. This is a salt. Here's a polar molecule as a solvent. That Na is going to dissolve away, and you're left with the OCH3 anion. All right, this is going to dissociate, in which this is going to be your nucleophile. And with that in mind, now we can see that it's going to behave as a strong nucleophile. So secondary, strong, what are we going to get? An Sn2 reaction. All right, so let's draw our substrate. Okay. Now, what is this going to look like? Remember, if you go back, if you ended up taking a picture of it before, but remember, an Sn2 reaction inverts the stereochemistry. All right, so we got one main product, but the stereochemistry inverts. All right, that chlorine, we started off as wedged. Given that it's an Sn2 reaction, we're going to end up being dashed. And there's your product. All right. So again, I really hope that this emphasizes the thought process that I want you to walk through. All right. Is it primary, secondary, or tertiary? If it's primary, then it's going to tend to be Sn1. No, if it's primary, it's going to be Sn2. If it's tertiary, it's going to be Sn1. But if you fall in that gray area, like this example, then you need to look at the nucleophile. All right, is the nucleophile strong or weak? If it's secondary and a strong nucleophile, you're going to have Sn2, in which your stereochemistry inverts. And if it's a secondary and a weak nucleophile, then you're going to have Sn1. Okay, so let's just say, hypothetically, I don't change anything other than the nucleophile. All right, so let's just say we have this. All right, the nucleophile or the solvent, sometimes your solvent is going to be the thing that you're going to be reacting with. All right, let's say we have this. All right, so secondary. So secondary, and this is a strong or weak. It's going to be a weak nucleophile. We're going to have an Sn1 reaction. Okay. What the products are going to look like is, again, we have retention and inversion for Sn1 reactions. So we're going to have the product that stays wedged. And it's an enantiomer. Which is dashed. Okay. So as an Sn1 reaction, this is a perfect example of producing a racemic mixture of R and S. Okay. So hopefully my goal here is to give you what you would need to know to determine an Sn1 and an Sn2 reaction and to illustrate what that looks like in practice. Okay. Let me see if I maybe have a couple more examples. Well, actually, let me illustrate the curved arrow. All right. So the curved arrow mechanism, let's just go back. So so it's really easy to illustrate the reaction mechanism for an Sn2 reaction. So I'll just go back to this. right? So this is just illustrating the curved arrow mechanism, all right? So again, just like acid base, you have to be able to recognize the directions in which the arrows are going to be going. All right, I can guarantee you, you're going to get a question about which of the following mechanisms or curved arrow mechanisms is correct for this following reaction. And if you just mix up which way the arrows are going to and from, you might just get led astray. All right, so remember, the nucleophile is the thing that's going to go replace where the leaving group was existing. Okay, so this is very similar to some stuff that we did with acid base. So the leaving group is going to leave and go onto the chlorine itself. So that's going to exist as a monatomic ion in solution now. And then your lone pair on your nucleophile is going to come in and make a bond with that carbon that had the nucleophile on it. Okay. So I just wanted to reiterate that because I can guarantee, at least on your test and in your practice, you're going to get a question about that. Okay. Something that I did want to touch on was intramolecular reactions. All right. That seems complicated, but I hope I can kind of simplify it in a way that will at least make a little bit of sense. All right, intramolecular. So these Sn1 and Sn2 reactions as two species reacting with one another are intermolecular. All right, but now we touch on something that will be intramolecular. All right, so let me just draw an example for you. Okay. And so let's say this is your question. All right. Now let's just assume that the question is what is the correct curved arrow mechanism to illustrate this intramolecular reaction. All right, remember, intramolecular is it's sort of occurring on itself. All right. So what's going to happen is, again, I tend to like to draw things out to make things explicit. It tends to help me, at least, in which if it does you, I recommend it. All right. So what tends to happen is that the nucleophile or there's going to be a species on the molecule itself that is going to behave as a nucleophile and it's going to attack itself intramolecular. All right, so what's going to tend to happen is that our leaving group is going to leave. All right, that creates partial positive or a positive charge or a carbocation. All right. And here we have a nitrogen with this lone pair that's going to act as its own nucleophile. All right, so you have a carbocation here, you have a nucleophile here. Okay, so the curved arrow would be the following. All right, so there's going to be a bond made in between that nitrogen and that carbon that the leaving group was on. All right, and this would get us the following product. in which that nitrogen is positively charged, but that's not very favorable. And we have a base that's going to come in and take care of that. All right, so we have OH. That's going to act as a base. And so this is a perfect example of tying back to some textbooks, chapter 3, of an acid-base reaction. That OH, that hydroxide, would love to become what? Water. So it needs a hydrogen. Where's it going to get that hydrogen from? One of those. Okay, so our curved arrow is going to go from our lone pair on the hydroxide to go take that hydrogen. And here we get the final product. Okay. All right, so this is a perfect example of what we call an intramolecular reaction. All right, you have a base, so you have the leaving group that leaves, and the other end is going to act as the nucleophile on itself. And if you have an extra hydrogen that's there on the species, you're going to tend to have a base that's going to come in and take care of that. Right, so let me move my head out of the way so that you guys can see the overall reaction mechanism, because that's important. You guys can take a picture of that if you'd like. And I think I have another example of this. Let me see. Cool, I do. All right. So let me share my screen, because that would make probably all of it. Hopefully you can share my, hopefully you can see my screen. All right, so what's going to happen here is, can I draw on this thing? Of course not. Well, I guess I'll be drawing it on the board. So we have this reaction mechanism. All right, not reaction mechanism, but we have this example reaction. Okay, so let me just go back and try to. All right, so let me draw this out since I can't draw on the screen itself. All right. So again, just like before, our leaving group is going to leave. All right. We have a carbocation. Okay. And so this oxygen is going to act as the nucleophile. So it's going to come in and make a bond with that carbon. So what that's going to look like pardon me, I'm far from an artist. All right. And again, we don't want that hydrogen to be there. All right, that's what's creating this positive charge. and we have a base that can come in and take care of that. All right, so this is gonna dissociate. All right, so our H minus is going to come in and take that hydrogen. Okay, and that bond goes onto the oxygen itself. So our final product is as such. Okay. Okay, so those are a couple examples of the mechanism behind the intramolecular reactions. All right, so hopefully that paints a decent picture of what that might look like, because I'm fairly certain that whether or not you're at FAU or any other university, you're probably going to get that type of reaction that's occurring. Okay. Now let me just double check if I do have another example. I know we've done a couple examples on Sn2. Let me see if we have an Sn1. So say we have this as a question, and it's just like, okay, well, what's the major product? Right, or what are the products? All right, so again, thought process. First and foremost, we need to look at the substrate. Is this substrate primary, secondary, or tertiary? It's going to be tertiary. Which is going to lead us to assume, which again, most likely, unless you have your professor that say, God knows why, they're going to say a substrate that's tertiary is going to be an Sn2. It's essentially always going to be an Sn1. All right, so primary Sn2, tertiary Sn1. All right, so tertiary Sn1. All right, so this leaving group is going to leave, and that solvent, sometimes in this case, is going to come in and take the place of that OH. And remember, Sn1s have retention and inversion of the stereochemistry. Okay, so we have a product that's going to stay as wedged like the OH was. And it's an enantiomer. All right, so retention kept as such, and inversion. All right, so again, this Sn1 reaction going to have a mixture of the two configurations, and we commonly will see this as a racemic mixture, which is, in a nutshell, a 50-50 mix of the two configurations. All right, so that's an example of an Sn1 reaction occurring, okay, again, following the same thought process, and it doesn't really matter what molecule it is itself, so long as you walk through the things that we know about this to lead you to the goal. All right. Now, some of you might get a question that have a chair. We all love chair conformations. All right. So this doesn't get more complicated, it just looks a little different. Okay. So say we have a chair. Oh, that chair was money. All right, let's just say we have a Cl. All right, let's say this is our substrate. All right. Let me draw what we're reacting with. So again, let's determine, in order to find the products, we got to know what type of reaction is occurring. All right, so is this Sn1 or Sn2? Is the substrate primary, secondary, or tertiary? It's going to be secondary. Right? That carbocation, 1, 2, bonded to 2 different carbons, secondary. All right? So that's that little bit of a gray area. Let's look at the nucleophile. Is the nucleophile strong or weak? Strong. All right. Hopefully that pattern in the thought process is starting to make sense, starting to click. All right. So secondary, strong, Sn2. Okay. So our chlorine is going to leave and our iodine is going to come in and take its place. Okay. But what this is going to look like looks like the following. All right. All right. It's not straight up, it's diagonally down. All right. What I like to say is that wedged is up, dashed is down. So let's just assume you have this chair. All right, this cyclohexane with the chlorine. All right. Wedged, if you were to redraw this as a chair, wedged is up, dashed is down. All right. So this should illustrate what we're getting at here. Remember, Sn2 inverts the stereochemistry. All right. So we can think of that Cl as being wedged. Wedges is up, dashes down. All right. So our I has to invert the stereochemistry. So it's not going to remain pointing up because that would remain as wedged. So we got to point it diagonally down. Okay. And vice versa if the opposite were occurring. Okay. So hopefully this provides I know this is a very broad stroke review of Sn1 and Sn2 reactions, but I really hope that this provides enough of information for you to get a kickstart. And again, the thought process, the logic that I want you to run through in determining if a reaction is going to be Sn1 or Sn2, and therefore what the products are going to look like in the products that you may or may not have. Okay, I really hope that helps. Again, please feel free to send me an email or message or whatever it may be if there's any other questions or concerns that I might be able to answer. All right, thanks guys.